So we're recording there now. So hi everyone, and you're very welcome back to our machine learning module here. Tonight we're going to be looking at convolutional neural networks. Last week we looked at neural networks in general, and tonight we're going to be looking at the convolutional version, which were a major step forward in terms of being able to make use of neural networks. And the reason that we required convolutional neural networks is because of this thing called the curse of dimensionality. When we have lots of dimensions in our problem, it just becomes so large that it becomes computationally impossible to deal with. And the big problem really comes when we try to do applications like computer vision applications where we're dealing with images. Images are big. You can consider them to be really big compared to other types of data. So they make other types of problems look like they're toy problems compared to image problems. The difficulty is that a single image, there's a huge amount of data, and this makes image problems very high dimensional. To have a hope of using images in machine learning, you have to be clever and to think about the special nature of images, and maybe look at some sort of redundancy that might be in there that we can take account of. So how many dimensions are in an image? Now, on the face of it, it appears that images are two-dimensional. But that's not how they appear to a machine learning model. So if they're color, you might think of them as three-dimensional. So you've got your two-dimensional two spatial dimensions, and then three channels for as the third dimension of the color. But again, that doesn't really tell the whole story with regard to machine learning. If we consider images that are, let's say, 32 pixels by 32 pixels by 3, with the 3 being the red, green and blue of your color channels, then from a machine learning point of view, this views it as if it's actually 3072, which is 32 by 32 by 3. So 3072 by 1, or a 3072 dimensional problem. So it's almost like it's looking at it as a single vector, and each one of these, the pixels, is a dimension. And that's for a very, very small image. You know, we're talking about a 32 by 32 by 3 image, which is very, very small. So we know that an image has two-dimensional structure in it. And what we mean here is that if we were to take the pixels from an image and were to mix them up and put them together in a different order, then we don't have the same thing. So clearly there's something about the structure of an image and where they're positioned in relation to each other that has meaning. Okay, so for that reason, we want to try and make use of that. Okay, just going to move this up here a bit. Okay, so the features are the dimensions are not independent of their position. So if we can in some way modify our algorithm to recognize this or make use of that redundancy, then we may have a means of tackling this enormous data problem. And the key insight here is the idea of spatial invariance. And what this says is that if we're trying to find something in an image, it doesn't matter where in the image it is. If it's there, it's there. It doesn't matter where exactly it's placed. And if we place a filter over it, we should get the same response. So no matter where in the image the thing that we're looking for is, if we place a filter correctly over it, we should get the same response as if it's placed anywhere else in the image. That's the idea of spatial invariance. It doesn't matter where in the image it's put. And the idea that cracked this was the convolutional neural network. So it was using this idea of convolution. So the idea is that you use a small filter, only a few pixels wide, and we'll show you examples of this in a few minutes, and you slide it over the image, applying it in each different position. The weights of the filter are still learned. Okay, so unlike in general image processing where we use filters all the time, but we come up with these hand engineered filters that we want, the weights are still learned like they would be in a dense network, but they learn the best response when every position in the image is taken into account. So as it's moved or slid or convolved across the image, it's going to see different parts of the image as it goes, but it learns from every one of those positions, and it finds the best response for finding the particular thing that it's looking for. And this means that the learned weights are shared by all positions. So it's not really that it just learns it in one particular position in the image. It moves around the image and it figures out what's the best weights that will find me the different thing that I want, no matter where it lands in the image. Now, one filter wouldn't do the job. If we just had one filter, that wouldn't be good enough because it would only find one thing in the image. So if there's a particular thing that's interested in, let's say it's interested in edges or corners or something like that, or maybe little blobs, well, you know, if we only have a single filter, that will only find that particular type of artifact, and it won't find lots of different ones that it might be looking for. So we can have many filters and they all learn to look at for different things, and that's then important when it comes to our initialization. We want to make sure that as we start to learn, all of our different filters go looking for different things. If we find that we have 20 filters and 10 of them are all looking for the same thing, then that's not making good use of our network. So we'd like our filters to all be looking for different things. And in practice, that generally works. You know, we generally find that they will go and try and find different things. So so if we have many filters that all learn to look for different things in the image, and because of convolution, they learn to find them no matter where they are in the image, and that's the idea. So what is convolution? Could I just get an idea from you, because I know some of you had a semester with me last year, some of you didn't. How many of you know what convolution means? You've come across the term before. Okay, so I'm getting lots of yeses there. I assume there may be one or two no's, but I don't know how many we have in tonight. We've a few more. So some people haven't answered there. Jerry's answering here. Yeah, Jerry's a no on this. Okay, so don't worry, Jerry, and Ratko's a no. You'll be seeing an example of them in a minute. But for some of you, you may have only come across convolution in terms of maybe image processing with me last year, or in terms of digital signal processing, and that's certainly the background that I've come from, which is digital signal processing. So if you come from a signal processing point of view, and I do, then convolution has a very strict meaning. And indeed, when I was first looking at convolutional neural networks, I got very hung up on this issue for the first few months that I was looking at them, until I had a kind of a key insight about them. So, and it was that they were using the term in a different way than I was strictly speaking used to. So convolution is the operation combining an input signal with the impulse response of a linear system in order to create an output signal. So it's a linear operation. It involves this sliding operation of the impulse response with the input signal to create an output signal at the correct position. It also requires that the impulse response, which we can define as the weights of the filter, it has to be flipped before the operation occurs. And we see this in DSP all the time. We go into quite a bit of detail on the whole idea of the thing, of the impulse response has to be flipped before you slide it across the signal in a one-dimensional sense. And if you're dealing with an impulse response in an image, we generally call this a point spread function, because it spreads out in 2 dimensions. And in this case, our convolutional filter has to be flipped in both horizontally and vertically. Okay, so it's flipped in both directions before you convolve it. And we'll go through an example shortly of the convolution itself, not necessarily the flipping. Now, there's another thing from DSP called correlation. So in signal processing, there's an operation called correlation. And this is where we look for a known signal in noise. And by noise here, we simply mean the part of the signal that's not of interest to us. So there's something in the signal we're looking for, and we have this kind of like, you can kind of think of it as a matched filter that we slide across the image, and we say, well, or a template, does it look like that? Does it look like that? Does it look like that as it goes across the image or across the signal? So to find the signal of interest, we take the template of what it looks like and we slide it across the signal, doing a multiply accumulate at each point as we go. So we're basically multiplying the signal at each point. Now, where the signal that we're looking for is present in the signal that we're analyzing, the template will line up somewhat randomly. But where it lines up, the signal of interest, sorry, I'm saying this wrong. Where the signal is not present, it just lines up with random samples. But where it is present, it lines up perfectly, and that gives a very large output at that point. And that kind of is an indication to us that there's a correlation between our template and the signal at that particular position. So we look at the activations above any activations that have gone above a certain level, and that suggests to us that we've found we found what we're looking for at those particular points. So a large activation occurs is the central position of where the signal of interest is. Okay, so these two things, convolution, correlation, they both involve this idea of sliding one signal across another and multiplying and accumulating at each different point. And the maths is almost identical. Okay, so the maths of these two is so similar that an algorithm written for one can be used for the other. The only difference between the two is that in convolution we do a flip and in correlation we don't. Okay, so that's the difference between the two. Now, just because they're the same mathematically does not mean that conceptually they're the same thing. Convolution is this operation that combines the input signal with a point spread function or an impulse response in order to create an output signal. Whereas correlation is looking for a particular signal in some sort of noisy signal. Okay. And so I give the example here of two things that are mathematically the same but not conceptually the same. If you're paid €20 per hour and you do 2,000 hours per year, you'll earn the same as if you get €2,000 per hour but only do 20 per year. I know which I'd prefer. I'm sure you do too, but your employer would probably say exactly the opposite. So the maths there is the same, conceptually not the same at all. And this is one of the issues that we have with convolution correlation. Of course, you can use one to do the other, but conceptually they're not the same thing. So what about the convolution in convolutional neural networks? Is it convolution or is it correlation? That's the question then. So the convolution in convolutional neural networks is a much looser definition. It simply refers to that sliding action. It does not refer to either of the other things. So it's not specifically convolution in the sense that we know it in DSP. It's not specifically correlation, although it's much more similar to correlation, particularly when we're talking about in terms of these networks that are used for classification and recognition. So it refers to the sliding action and is a looser definition. We don't do the flip, but importantly, we learn the filter weights. Now, if we're learning the filter weights, there's nothing to stop if the flip should have occurred, in other words, if it's definitely doing a convolution, that it can just learn the flip into the weights. So it just learns the weights in the opposite directions than it would have done otherwise. Okay, so we can't guarantee that the flip is not occurring, that it's not just learning it in. So the filter could just learn the flip if that's what was required. So conceptually, are we doing convolution or correlation? This is not clear. In recognition, particularly classification type networks, this is much more like correlation because what you're doing is you're looking for particular types of things at each different layer. That creates an activation, and at the next layer you're saying, well, okay, where do those activations occur? And you're looking for things again and again and again until you're eventually looking for very large items across the image, like, is there a dog in this image? Is there a pedestrian in this image? Is there a vehicle in this image? Now, in things like generative networks, which I'm not unfortunately going to get any time to cover with you in this module, but they're a very interesting area, and it's the idea where you use convolutional neural networks to generate images rather than to just find things in images. And in those, then the convolutional operation that's happening there is much more like the convolution that we see in digital signal processing, in that you're maybe creating some sort of an image process, an output image given an input image, and you're making some change across it. Okay. So I just want to make that clear. It may have been that it wouldn't have caused you any confusion one way or the other, but certainly for anybody that comes from a digital signal processing background and understands convolution well, it can cause quite a bit of confusion, and that's why I just wanted to mention it there, so that you're not too confused by it. So it's a looser term. The second thing is convolution is a linear operation when we talk about it in DSP. So is it a linear operation in convolutional neural networks? So at an individual layer where the convolution takes place, that operation itself is linear, but it then passes the activations through an activation function, which is a non-linearity, such as a sigmoid or a ReLU or a few others, and we'll I don't think I talked about them last week. I think I'll talk about them next week. I've forgotten now which order I'm doing things in. Did I mention the activation functions to you last week? You can remind me. The sigmoid and the tan H and that. I don't think I've come to it yet. Nobody's answering, so I expect to have. I know it's somewhere in the notes. I just haven't come to it yet. So it's passed through a nonlinearity is the point, and because it's passed through a nonlinearity, at that point this is no longer a linear operation. So even though we have this sliding operation going on here, we are passing through a nonlinearity, and then there's often this sense where from one part high up in the network, we're looking down through several of these layers, and we have a receptive field. And you can think of all of this as sliding across the image in some way. Again, this is not convolution in the strict linearity sense because of the fact you've got all these non-linearities in between. So once again, we're going to this looser idea of convolution as just being a sliding operation. So some refer to the idea of many layers sliding across the image. In this case, the linear operation of convolution has no real meaning. There are these things called fully convolutional networks that allow for the entire network to slide across an image. So where we might start with an image that's only, most networks will take in an image maybe of something like 256 by 256 or something smaller than that. If you have a much larger image than that, you might want to slide your entire network across that image, creating outputs as you go, and then in some way trying to determine whether you found things at these different points. Again, we're just talking about that sliding action in that case, and we're not including the other parts of the definition of convolution. Okay, so for those of you who haven't seen convolution before, I'm going to show you the sliding action here. And what we have here is, so on the left here we have an image, and it's just a 5 by 5 image, so it's a very small image. Then what I have is I have a 3 by 3 filter, and my 3 by 3 filter is as follows. Each of the pixels around the outside are all -1, and the one on the inside is +8. So they're going to basically cancel each other out. And what I'm basically looking for here, this is a type of edge finding thing where I'm going to find where the current pixel is different from the pixels around it in terms of a result. Now what happens is that we place it on top of the image like so. Okay, and in this case what we would do is we would multiply the 11 by -1. Okay, so you can see here the sorry, I'll use this. We'll multiply the 11 by -1, and we can write that down, you know. Actually, sorry, I realized I've done something here, so I'm just I left the top of my filter behind me. Okay, so let's say that would be something like 11 multiplied by -1 plus 44 multiplied by -1 plus 66 by -1. And this continues. You have the 14 by -1, the 64 by -1, the 16 by -1, the 74 by -1, and the 66 by -1. And you finish by adding the 76 by 8. And you see whatever result you get. And basically what you then do is you create a new image here. Okay, so you create a new image, and in its first pixel you're going to put the result of that there. And then what you do is you slide over to the next position, and you go and you do the exact same thing again, and you continue to do that. You slide to the next position, and that creates the next position here and so on. And then you move down the image and you move to this one and to this one and to this one and so on. So you slide across it. Okay. So, and I'm sure some of you have questions about what happens this one. What do I do for this one there? We're off the edge here and so on. So there's a lot we still have to have a think about what's going to happen in certain cases. Now, in many, you know, obviously for most images, we're dealing with a much bigger than a 5 by 5 image. So you see the extreme case of what's going to occur here. But you kind of need to look at a small case so that we can see the sliding going on. Now, some nice people have created some nice animations of this thing happening that are a little bit better than me just sliding the thing across the image. So there's the Theano Convolution Arithmetic Tutorial. Now, Theano is a piece of software for developing deep neural networks. So it's a kind of a competitor to TensorFlow. But they have a lovely set of explanations, and you can see a lot of little animations there as well. The other one is this guy Martin, and I assume that's pronounced Gruner, but I'm not certain, so apologies to Martin if I pronounce his name wrong. But I found his GIF or GIF, whichever way you pronounce it, on a web page, and then I got it very difficult to get back to his original where it was originally done. So I have a link there, but the link only gets you so far back towards the primary place that it was. Now I have the GIF actually opened on my machine here, so you can all see that, right? Now Martin has done a nice little GIF, but it's open on my Mac in terms of the individual images here. So you can see the sliding operation that goes on here as it slides across. This is a 4x4, but importantly, because this is going through an image, a red, green and blue, we also see what happens in a convolutional neural network here, which is that the sliding operation happens in the X and Y, but you must go through the entire depth of the image as well. So if you have a 4x4, I had a 3x3 in my previous example here. We have a 4x4 here, but it's actually a 4x4x3 because we have to go through the entire depth of the channels of the red, green and blue. As we get further up in these deep neural networks, we end up with far more channels than just 3. We'll often end up with hundreds of channels. And the important point is that we might have like something like a 3x3 filter, but it has to go through the entire depth. In general, we don't slide convolutionally through the depth. I'm sure people have tried it, and I think there are papers on people who have done it. However, in general, this redundancy that we talk about makes more sense across it spatially in the image rather than going through the channels of the image in a convolutional manner. So you can see what's happened here, that for a particular filter, this is called W1. It's not very obvious, but if you look carefully where he has the W and then the brackets, there's a little tick down just below the W there. That's to tell you that it's filter number 1. So we can watch as we build up our activation map here. We have each of these little circles down here are basically the activations that are coming out after it gets multiplied and accumulated by all those values. You can see what's happened here. We've gone off the edge, and he's mentioned a thing called padding there. I'll be talking a bit more about that in a few minutes. And we go through the entire image in that way. And what we then do is we create a new filter, which we'll call W2, and that goes and creates effectively another channel for us now. So if we create many filters, what we'll do is for each of those, let's say we create 20 filters, we go from having a red, green and blue image to having a set of activations that tell us that we maybe have 20 channels in it. They're no longer red, green and blue. What they're telling us is this filter for a particular, one of the channels tells us this filter, here's what it found and here's where it found it. And then the next layer tells us what the next filter found and where it found it. So if we have 20 filters, we'll have 20 things that we've found and where we found them. Okay, so that's the idea. That hopefully that little animation makes it a little bit clearer how it slides across the image. Okay. So let's have a look at maybe some of the original networks that came out. So his first one is called the LeNet. It's named after Jan LeCun, and very, very high profile guy in deep learning. Mainly, obviously, because he's done a lot of work in the area, but also because he's so famous for having introduced the idea of the convolutional neural network. So he introduced it in 1998, and it was the first successful use of a convolutional neural network. It was successfully deployed for use in postal services for reading handwritten postal codes. So it would be quite a while before they were able to scale this up to look at fairly significant images. So you can see the idea. This is the way he's looked at the network. He's got a 32 by 32 input, which is a very small image, and he's got his different filter outputs here. So you can see that this is the output of one filter, this is the output of another filter, another one. He's got 6 of them all together. From that, he does more convolutions, and he's got another 6 of them here. And that goes on. In the next one, he's got 16 of the filter outputs of different things that he's looking for within it. Okay. The other thing we notice is that the image gets smaller as we go down to 14 by 14, then down to I think just 5 by 5, and then he has a few what we call fully connected layers before determining what the output is likely to be. In other words, determining what letter or what number we've got. Okay, so that was one of the first ones, but as I said, it'll be a while before we'll be able to use this at scale. Then along came the AlexNet. Now, a lot of these networks are called after the people who wrote the paper, and they were not necessarily called, you know, in the original paper where this was written, it was not called the AlexNet because it's called the AlexNet because the person who wrote the paper is Alex Krzyzewski, and the same with LeNet. Was probably not called LeNet in the original paper. It's other people called it LeNet afterwards in order to give the paper a shortened name. So AlexNet in 2012, this was a breakthrough convolutional neural network, and it was by Alex Krzyzewski et al. And he created a network that won the ImageNet challenge by a huge margin. So this was the first time that a convolutional neural network had won the ImageNet challenge. I don't know was it the first time they tried it, but it was the first time they'd really got it working, and it won by such a significant margin that nobody's ever won the ImageNet challenge without using a convolutional neural network. Again, this network looks extremely complex, but one of the reasons that it looks so complex is the fact that GPUs at the time could not fit this neural network in its RAM. And so what they had to do is they actually had to split the image across two different GPUs, and that's why you see it as two separate networks. It makes it look much more complex than the network actually needed to be, and that's why the image of it here is slightly more complex than you're going to see in some of the future architectures that come along. So let's have a look at an individual filter and how it works. And what I've done here is I've done a 5x5 filter, and it's going to convolve across a 32x32x3 image. So we've 32x32 pixels, and we've got red, green, and blue as our depth. And you can see that our 5x5 filter here has to go 5 across, 5 down, but it has to go through the full 3 of the depth. And that's going to produce an individual pixel here. And as we slide it across the image, we're going to get 28x28 pixels. Now, the first question you might wonder here is, how have we gone from 32 down to 28? So we've gone from 32x32 down to 28x28. And the reason that has happened is that we have to have numbers to multiply these things by. So if we go back to my example here, when I was sliding this across the image, you can see that I had to be fully immersed in the image in order to create an individual value. So I've got 1, 2, 3 before I have to go down to this 1, 2, 3, and then 1, 2, 3. If I go beyond that, I've gone off the edge of the image, and I won't have anything to multiply these -1s by along the side. Okay, so this is the idea of being fully immersed within the image. So you can see there that my 5x5 would actually produce a 3x3 at the output, simply because on the edges I would have nothing to multiply it by if I went out here. So in the case of a 5x5, as we have the example here, we have a bigger problem again. So there'll be basically, we have to go 2 pixels in both the X and the Y before we get a legitimate value. And that's why we have lost 2 pixels off either side here. 2 pixels off that side, 2 pixels off that side. 2 and 2 is 4, so if we add 28 and 4, we get 32. And we've lost 2 pixels on either side there as well. So that's why we've ended up with the 28x28, and we'll look at ways around that in a while. So filter is a 5x5, but must be the same depth as the input, so it has to be a 5x5x3. So altogether, in terms of parameters there, you're going to need 5x5x3, and you're going to need a bias parameter which adds 1 to it. So 5x5x3 would be 75 altogether. Add a 1 for a bias is 76 weights. So for each of these filters, we require 76 weights, but bear in mind that that's going to create an activation that's 28x28x1. So it's going to create, so it's much bigger than what you would get if you tried to do this with something like a fully connected layer in terms of the number of filter weights that produce an output. So we slide this across the width and the height, but we always use the full depth. It will produce a 28x28x1 activation map. So this is what we refer to as an activation map here. Again, this will be, you can kind of think of this like a heat map, or in other words, it will have values, but it won't necessarily have values that are nicely in a range for us to look at as an image. So if we want to see this, if we want to see it pictorially, we'll have to do some scaling of those numbers so that it fits into the nice 8-bit grayscale images that we're used to looking at. There would be no point at looking at this as like a color image, because we've lost our color information at this stage. We simply have brightness values now at this stage and only a single activation map. This is for a single filter. If I want to look for other things in the image, then what I do is I create another filter, which again is going to take me another 76 waits to do, and I'll create a second activation map to go on this. So firstly, while we can view the activation map as an image, this is simply a convenience. What we really have is a new representation of our original color image. The change in representation has been brought on by a 5x5x3 filter. The representation is the similarity at each point in the image, the similarity between the learned filter and the underlying image. So remember, like correlation, we're looking for things in that original image here. But what are we looking for? Well, at first we don't even know what we're looking for, so our filter is going to look like pretty much nothing. And it's only when we start to change those weights to look for something that our final algorithm at the end can say, oh, do you know what, actually that's very useful to me in terms of determining what's in the image. Keep doing what you're doing, or go further in doing what you're doing. And by doing that, we learn weights that learn to look for particular things in the image and learn to activate by a large amount if it sees a particular thing in the image. So you can see how it tries to learn this across the entire image. So what we really have is a new representation of our original color image. The change in representation has been brought on by this 5x5x3 filter. The representation, as I say, is the similarity at each point between the learned filter and the underlying image. The values in the activation map will not naturally have values that make it easy to display as an image. So they won't be nicely in this range of 0 to 255. So they will normally have to be scaled for viewing on a computer. Now, we scale them to view them on a computer. That doesn't mean we go and change them to that. We'd still like to leave them the way they are for the rest of the network to understand them. We can also look at the output before or after the nonlinear activation to see what happens before the activation, what happens after it, to see what it accentuates and what it removes. And we'll see an example towards the end of that. So we'll see what effect the activation map has on it. And of course, we can have multiple activations. What I've done in this case is I've shown a 28 by 28 by 10. So that means we're going to have 10 filters. And we could figure out that this entire layer would require, because we had the 5x5 by 3 on the input, and we add 1 to that, and that was going to give us, as we say, 76. And we multiply that by the 10 of these that we want, because we're going to have 10 filters, so that would require 760 parameters altogether. So parameters is basically the number of multiplications that we're going to require as well in order to do the job that we're going to do. So a single filter can only learn to look for one thing. Obviously, we want to look for many things, therefore we will have many filters. Let's assume we decide, this is, remember, a hyperparameter, to have 10 filters. So that's important there. The number of filters is a hyperparameter. You have to choose how many filters you want to have in your architecture. And having, you know, how do you know that you've enough filters? Well, one way to tell is if you look at the activations and you start seeing that a number of the filters are coming out the same. That suggests that either there's something wrong with the way the thing is operating, or in that it's learning the same thing in each case, or you might have the situation that that there's simply nothing more to be learned from this network, and therefore multiple of your filters are learning the same thing. So that's maybe one way that you can try and determine, but that basically means that you've got to have enough filters in order to be able to see that you've gone over it. You'll never learn from going under. So let's assume that as a hyperparameter we've chosen 10 filters of 5x5x3, then we'll get 10 activation maps. These 10 activation maps can then be thought of as a new representation of the data. So now, rather than seeing the data as red, green and blue, we're now seeing it as these 10 different activation maps. So instead of 3-channel image, we have a 10-channel image. So let's take an example here where we've got two layers in the network. So we've got a layer here and we've got a layer here. So we'll call this layer 1 and layer 2. So it has 3 by 3 filters, but because layer 1 has 10 channels in it, we have to have 3 by 3 by 10 because we have to go fully through that. That's going to be 9 by 10, which is 90, and we add 1 for a bias as well. So each of the filters in my second layer are going to have to be take up 91 parameters to just do a 3 by 3. Had we chosen 5 by 5 for my second layer, then we would have a 5 by 5 by 10, which is 25 by 10 is 250, and add 1, we'd need 251 parameters rather than the 76 parameters which we needed for each of the filters in layer 1. Okay, so that's the first thing, and as you can see, I've got more activations in my second layer again. So one of the questions I'd asked here is how many parameters at layer 2. So in total, at layer 2, obviously for each filter I would require this first one here. In total I require 91 for each filter in layer 2, and I've got 20 filters. As you can see, I've got 20 filters there. So in total for my layer 2 I would need 91 by 20 to tell me the total number of filters that I would require. Okay. Which is 910, which is 1820 filters altogether. Okay. How much memory would I require at layer 2? Now the memory is referring to the number of activations, and so layer 2 is 26 by 26 by 20 in terms of its activations. So you can think of this as if this were an image, how much space would it take up? So it's 26 by 26 by 20 is what that would require. Okay. My calculator close by, but you can I do have it, I found it. 26 by 26 is 676 pixels in each case, and then we multiply that by 20, and that comes out at 13,520. Sorry, 13,520. Now, how big is each pixel? In the original image, each pixel in a specific channel would only require 8 bits or 1 byte. And if we're just using 1 byte again, well, this is 13,520 bytes. If we require 2 bytes to store that, maybe because we're using floating point numbers and we're using 16-bit floating point numbers, then we would require twice that. And if it was 4-byte floating point numbers, we would require 4 times that. So there are all sorts of decisions that you have to make with regards to how much memory you have on a particular system as to how many bytes you're going to use to describe each of your activations. Oftentimes in training they might use more bytes than they would use during inference, where they maybe try and quantize it. Okay, so that's just maybe to give you an example. So some of the calculations. So one of the things that you can do is that you can determine the width and the height of the activation map that's coming out by using the following. We use the width from the previous layer, and we subtract from that the size of the filter. And the filter, let's say if it's a 3 by 3, then your f there is going to be a 3. Okay, if it was a 5 by 5, your f is going to be a 5. What we then do is we include on top of that how much padding we're going to have, right? So I'll discuss the padding in a moment, but the padding is basically how many pixels we put around the outside in order to make sure that we can slide our filter off the edges. Okay, and then we divide by the stride, and the stride basically is how many jumps we do between each one. So again, I think I covered that in a moment. Maybe I don't. Yeah, I do. Yeah, I covered it in a few slides time, so we'll come back to it. And then what you do is you add 1 at the end. Okay, and then the depth at a new layer is basically the number of filters that you have at this layer as well. So just be aware that we're dealing with the current layer, and the L-1 is the previous layer, is what we need for that. Okay, so that's it, and you can come back to this formula at any point when you want to figure out. We'll talk about some of the different points in this. So the question then was that when we had this filter, what do we do at the edges? What do we do when we wander off the edges here? Can we do something about that? So some of the different things that we can do is we can pad it. We can put zeros all around it, like this. Okay. So I'll just, that'll do me for the minute. I don't want to draw them all in. Actually, what I'll maybe just draw 1 or 2 more in, 0 and 0. And you can see here that what this will do is, this will allow us to do the number 11 here, because what we don't want to do is we don't want to be multiplying the -1 by nothing. We don't want to wander off the end of an array. Basically, it's usually trouble. So if we put padding on the end, this won't exactly give us a correct answer, because you're still gone off the edge of the image, but it will at least give us a value for this first pixel, which we wouldn't get otherwise. And if we do this, we can maintain the size of the input image. So if we do this now, I can do 1, 2, 3, 4, and 5, and I have something to multiply it by in each case. And so if we do that, we can maintain basically the size of the image on the output. So unlike the previous case, when we went from 32 down to 28, we would go 32 to 32. If we have a 5 by 5, you can see the issue that we're going to have. We're going to have to include another set of zeros outside of that. Okay, so like that. So that basically a 5 by 5 image would then be able to sit with this as its center spot. So that if we look at a 5 by 5 here, it'll go down that way. And that'll be our 5 by 5 that'll happen there. So we'll have to include an extra set of zeros in each case. So this is 0 padding. This is the example that we have here for the 3 by 3 case. As I say, with 5 by 5, we'd have to put another set of zeros around this in order to make this work and have the same size of an output set of activations as the input. The other options, and these are very difficult to see, but we could just repeat the same number again. And some people prefer to do this. So rather than putting in a 0, they prefer to take the closest pixel to them in terms of a repetition. And so our original image here is this 5 by 5 here. Have I put it in the correct? I have, yeah, so just color it in there. It's a 5 by 5, and what we're basically saying is, in each case, what we're going to do is we're going to take the closest number to us, which is that one there, and we're going to place it there. Closest number to us here is the 44, so we'll put that there, and so on. And you can pad it all around by doing something like that. And what I've done here is I've done this for something like a 5 by 5 filter to allow us to include that. So I've put 2 values on the edge to do it. The other one is something like mirroring, where we mirror across the image. So what we basically say is, okay, mirror that 11 there, and then this 44 should mirror that value in there. And same as this 44, same as that 44. I think I've done this wrong. That should be a 76 mirroring that one. I knew I'd make some mistakes somewhere in this. Yeah, I think I've done that wrong for a few of them there. But I did it correctly down here, 15 for 15, 34 for 34. So I figured I'd make some mistakes in doing that, because it's very difficult to actually write out those numbers and get them right. Okay, so that's some other options for what to fill in those spaces if you're going to be going off the edge. Going back to our example back here, you can see what happens when he goes off the edge here. That's you can see off the edge there, and going off the edge on the other side, we've gone off by. Sorry, I'll do it again. Yeah, you can see he's gone off 2 pixels off the edge there, and then 1 pixel off the edge, and then fully immersed in it. Okay. So, a few questions on this, and we'll see if we can get these right. So I don't know why I noticed this about 20 minutes before the lecture. I'd written the numbers 2 and 3 here instead of 1 and 2. I've no idea whether I had something in my head there that I wanted to do, or whether that was just a mistake. But it should be 1 and 2 is what I'm looking for here. So we've an input image that's 32 by 32 by 3, and we have a layer 1 has 10 filters of 3 by 3. Now all I've said is 3 by 3 here. Always assume full depth, so it's normally not specified. Okay, so what would this would be 3 by 3 by what? Does anybody want to tell me what that should be in my first layer? What would be the depth that it's looking for? Okay, so Blohin's going for 3. Anybody agree or disagree with her? Okay, you should have stuck to your guns there, Blohin. You were right in the first case, okay? So the important point here is that we have an input image that's 32 by 32 by 3. Our layer 1 filters are going to have to go into that. So just like back here, we have to go through that full 3 there. We have to go through the full range of that. So it'll be 3 by 3 and the full 3 there, okay? So you always look for the depth, you always look for the filters in a layer, you look for what were the depth of the activation maps that came before it. So it'll be 3 by 3 by 3, okay? So layer 1 has 10 filters of 3 by 3 by 3, and layer 2 has 20 filters of 3 by 3. Now, what will be this one? What will go on this one, do you think? So you need to look at what was the size, what was the depth of the activation map of the layer before it. Okay, no, yeah, you're including the 1 for the bias. That's fine. Just be wary. You've said 3 by 3 by 3 by 10. It's just 3 by 3 by 10. There's no that other 3. That's got dropped off in the previous case. So in this case, what we'll have is a 3 by 3 by 10. In other words, we used the number of activation maps in the previous case. The fact that that was 3 there doesn't get carried over into the next one or anything like that, right? So just like back here, where we had 5 by 5 by 3 to go through the entire depth of that. And then in this next one, we have a 3 by 3 by 10 is what we're going to have, okay? And then, of course, you are correct to say that we, if we're talking about the number of parameters or the filter, we will add 1 for a bias. Oftentimes people leave that out, but I think it's important that we do remember that the bias will take place there. So what are the dimensions of layer 1 if no padding is used? So do you want to take a guess at that, or maybe rather than a guess, a calculated answer? What are the dimensions of layer 1 if no padding is used? Now layer 1, when we refer to layer 1, we're referring to the activation maps that come out of layer 1 after the filtering of it. So we've one answer so far. If anybody else wants to throw in their threepence worth. I like it when we get a bit of disagreement. That's always good. Okay. So that wouldn't kind of find I there may be some confusion in what you mean there. That is total number, but we'd like to break it up into that. So you're basically saying it's 32 by 32 by 3 is what you're saying there with that one. And I prefer you showed it as that, if that's what you're saying. Okay, it's not the right answer, but nobody else seems to be typing something in. So layer 1, we need to describe the activation maps of layer 1. Now the first thing is we have no padding, which means that to be fully immersed in it, we're going to lose a pixel off either side because we're doing 3 by 3. Unlike what LG is saying there, we're not going to lose 2 pixels off each side. Now I know in the example back here we dropped to 28, but that was because we had 5 by 5 filters in that case. We've only got 3 by 3 filters in this case. So you can see in the case where we had 3 by 3, we went from 28 down to 26. We only lost 1 off each side rather than 2. So what that basically means here is that we're going to have so what are the dimensions? We're going to have 30 by 30. We can't leave it at that because we have how many filters? In layer 1 we have 10 filters, which means we're going to have 10 activation maps. So that's going to be 10. Okay, so that's going to be the dimensions of the output. So what we're effectively talking about here is we're talking about how big that output box is going to be. Okay, so the entirety of the box, which means we need to give 3 dimensions in terms of that. Okay. Does everyone understand where that came from? Yeah. Okay, so I'm going to ask you then for the second one. What are the dimensions of layer 2 if no padding has been used? So we know the dimensions going into it are 30 by 30 by 10. What are the dimensions of layer 2? Again, we're using 3 by 3 filters. Okay, so I'm conscious of the time, so we're gonna push you on this. Okay, so we're gonna lose one off either side of this, so it's gonna be 28. Sorry, 20, I don't know why I wrote 22. 28 by 28. How many filters have we got? We've got 20, so our output activation map is going to be 28 by 28 by 20. It's going to be the full size of it, which I think Blohin has correctly written there. Okay. How many multiplications are required to create layer 2 activations, not including the activation function itself? Now, multiplications is basically by the number of parameters. So let's have a think about how many parameters are we going to have in layer 2. That's really what this is asking. Now, we've got 3 by 3 filters in layer 2, but they have to go into they have to go through the 10 activation, or the 10 channels of layer 1, so they're going to be 3 by 3 by 10. And I think even Blohin was mentioned, or somebody mentioned it earlier, did the +1 here as well. So we're going to add 1 to that. So that's going to be 3 by 3 by 10. We are at layer 2 here, aren't we? So 3 by 3 by 10 is going to be 91. And how many of them have we got? We've got 20 of them. So you can figure from that, that's going to be 91 multiplied by 20. It's going to give me 1800 and... Sorry, I didn't include... Yeah, I did. 1820 multiplies is going to require... Sorry, this is the number of parameters, right? So that's how many we're going to require to do each pixel full way through the depth, right? But what we're then going to have to include in that is the actual size of the activation, which is going to be... So you can kind of think of this as 91 by 28 by 28, because it's going to have to do that. I haven't done that calculation, so 28 by 28 multiplied by 1820. Okay, so it's going to have to do 1.42688. So almost 1.5 million multiplications that are going to be required for it to create that full activation layer at the output. So this is it needs 120 parameters to do it, and it's going to reuse those in 28 by 28 multiplications, or 28 by 28 times. So that overall it'll be 1.4 something million multiplications that are required. Okay. This is why we require things like GPUs and so on to do this. Now, we mentioned this earlier, the stride. One of the things that we can do is we can decide, well, I'm going to jump from... I'm going to do that calculation, and then I'm going to jump immediately to here and do this calculation, and then I'm going to jump immediately to here and do this one, and jump immediately to here and do this one. Okay, so this is the stride. How many jumps we make between each calculation. And to some extent, this also gives us an impression of the overlap between these filters, that where you can see here that this one overlaps to a large extent with the calculations for the next one and for the next one. So stride also, people oftentimes describe it as the amount of overlap that's going to be between some of these different filters and so on. So we can decide to have a greater stride than just a stride of 1. And if you remember back to our calculations back here, our stride here tells us something about the output, the size of the output that we're going to get. So in terms of stride calculations, what we do is we take n, which is the width or the height. We subtract from that the size of the filter. Let's say it's a 3 by 3. We just put in a 3 there. And we divide by the stride and add 1. And that will tell us how big the output is going to be. What you need to be careful of here is that if you do this calculation and you end up with a non-integer, you're going to have a problem where your image is imbalanced. So you need to make sure that whatever way you do it, that you come up with a stride and a filter size that makes sure that you get an integer out of this full calculation here, or otherwise you're maybe going to have to do a bit of redesign of your architecture to make it all fit. So if we have an input image of 32 by 32 by 3, layer 1 has 10 filters of 3 by 3, always assume the full depth, so it's not normally specified as I said. Layer 2 has 20 filters of 3 by 3. What are the dimensions of the activations out of layer 2 if we use no padding and a stride of 1 for both layers? I think we've already done those calculations actually on the last thing. But you can see here how if we just do this, we can do this fairly quickly here. So for layer 1 here, we had 30. Sorry, layer 1 is 32 minus the size of the filters, which is 3, divide by a stride of 1 and add 1 is going to give me 29 plus 1, which is 30. And that's what goes into layer 2. So we do 30 minus 3 divided by 1 plus 1 is going to give me 27 plus 1, which is 28. And that's what we calculated as our outputs. Just be careful. Let's say, for example, that I decided to use a stride of 2 in any of these cases. So that's 32 minus 3 divided by 2 plus 1. You can see that what we're going to end up with here is we're going to end up with 29 divided by 2, which is going to give us a non-integer. And then we add 1 to it, which will still give us a non-integer. So we've got a problem there. So you're going to have to decide to use something like maybe a 4 by 4, which is perfectly fine. You can do a 4 by 4. That will give me 28 there. 28 divided by 2 is going to give me a 14 plus 1. It's going to give me a 15 by 15 output in terms of the size of the activation. Okay. So that's our stride, and you can see how you use that stride as well earlier in these calculations here in order to get the overall size of the width and the height of the output as well. If you're using padding, you use that other one, and if not, you can use this one. Okay, there are some popular filter sizes, generally 3 by 3, 5 by 5, 7 by 7. We don't generally like the 4 by 4s and the 2 by 2s as much because they're not symmetrical around the pixel that we're looking at. They're always going to be slightly off there, but they do find uses as well. So in generally, if we're going to be doing a stride of something like 2, we like to have an odd number of width by height in our image in order to bring it down, and you'll see some examples where they start with like images sizes of 227 by 227 rather than 224 by 224 for that reason, because they use different strides. So in general, filter sizes 3 by 3, 5 by 5. 7 by 7 and higher are used on occasion but are much more rare, and indeed I've seen 11 by 11 and things like that, but that's using a lot of parameters. 1 by 1 is also useful, and that can seem strange at first that the 1 by 1 might be useful because it's not a point spread function at all. But do remember that when it's a 1 by 1, it's still 1 by 1 by whatever the depth is. So if the depth was 10 through the thing, it's still a 1 by 1 by 10. And what you're now doing is you're creating a new activation map that's created from all of the channels in the previous case. So you're combining those together and saying what weights combine those together well in order to say, well, if I had this filter output and I had this filter output and both of them were firing high, does that suggest that the two of them together suggest something? And these 1 by 1s are very useful for combining those together. Indeed, in ordinary image processing, this would be a point operation only. It wouldn't make sense. However, we should remember that convolution applies to the full depth of the previous layer, and as such, a 1 by 1 filter is another way of combining a weighted average of the activation maps in the previous layer. So if, for example, we expected out of our 10 filters that 4 have high activations in the previous filter maps, then we'll get a high weighting in our 1 by 1 filter for those 4 particular activations and low weightings for the other ones in terms of trying to find something. Now, there's this idea of a receptive field, and if we have a 3x3 filter, we have a field over which we receive information from of 3x3 pixels. If it's a 5x5, it's over over 25 pixels, or 5x5 pixels is the receptive field that we receive things from. However, because in a convolutional neural network we layer these things on top of each other, we have a situation where an activation here has a 3x3 field in this one, but each one of those 3x3 had a 5x5 field that it took things from. So what is the overall size of the receptive field in the original image that a pixel in, let's say, our second layer here would see through all of these operations? So basically the situation that we have here is, if we take something like a 3x3 here, and from that we had each one of these took from a 5x5. Okay, so we'll draw that there. Okay, so now this one took from a field going that bit further out. If we then take something like the, we'll do a red one here. This pixel here, this would have seen everything going out to there. And if we take some other color, sorry, go for maybe a green. This one would have seen everything going down to there, and so on. So what is the receptive field that it's seeing here? Well, in actual fact, what it's seeing is 1, 2, 3, 4, 5, 6, and 7. So it's going to see a 7x7 because of the fact that we've gone back to a 3x3 and then a 5x5. Okay. So we can actually calculate the receptive field in that way. And what this is basically saying is that this is a mechanism whereby the deeper you go with your network, the higher up layers can actually see things in more of the image than the simple 3x3 or the 5x5 would have seen. So it can see larger objects and can take information from a larger receptive field by doing that. So it may seem that these small filter sizes will not be able to see much large structures in an image in order to be useful. However, as the layers increase, then the receptive field of even the small filters increases. You can consider the activations of layer 2 of the network on the right. What is the receptive field of a pixel in this activation layer? And what we've just shown is that it would actually be, it would see a 7x7 region in our original image. And if we went further up and further up, if we kept going up in filter sizes that kept having 3x3s, we'd go up by one. We'd go from 7x7 to 9 to 8x8, 9x9. It would go larger as it would go in that sort of direction. There's a nice little online tool there for calculating the receptive field for things at particular layers, and you can see how it affects it and changes it. So on the previous slides, layer 2 used a 3x3 and layer 1 used a 5x5. So layer 2 has a 3x3 receptive field of the pixels of layer 1. As each pixel in layer 1 has a 5x5 receptive field of the input image, then the pixels in layer 2 have actually got a 7x7 receptive field of the input image. Admittedly, through all those non-linearities and things like that, so that has to be kept in mind. Now the question is, would it be better to have just a single layer with 7x7, or is it better to have like a 5x5 and a 3x3? And the question is that it is not, or the answer is it's not better to have a 7x7. The 7x7 will use far more parameters than the 5x5 and the 3x3 in two separate layers. That's the first thing. You can, and I would advise you to, I won't do it for you here, but I would advise you to calculate through that and make sure that you're happy that that's the case. Whereas, and the second thing is the 5x5 goes through a non-linearity before it goes to the 3x3. And that means that because of that non-linearities activations, they add a huge amount of complexity to what your model is able to model. Okay, so what it's able to model is hugely affected by having a non-linearity in there. So having a 7x7 linear layer versus a 5x5 going through a non-linearity and into a 3x3, actually that second one has much more power in terms of describing what's going on, and still looks at the same size receptive field. So there is a trend, and you'll see this. There's a very famous network called the VGG. I'll talk about it, I think, next week. And it used the idea of just having all 3x3 filter sizes in each of the different layers, keeping the network in terms of its architecture as simple as possible. And the idea is that by stacking lots of these layers, that you got wider by a layer, by 2 pixels, basically 1 pixel on each side, as you went up through the network. So the receptive field going all the way back ended up being quite large by the end of it, and it was just this simple idea of having constantly 3x3 filters, but changing the number of filters and the number of activations in each case. So there's a trend towards stacking 3x3 filters in several layers, and it's generally popular, more popular than using larger filter sizes. Now, this thing, pooling, one of the things we've discussed in previous lectures is the powerful idea of representational learning. So at each layer, we learn something more. Now, I see here we've also talked about the power of dimensionality reduction, but I actually don't think we have talked about it much. The reason I have that there is that I had originally planned to give you a lecture on principal component analysis, and as I said, I kind of dropped that when I seen how many hours that we had and what I deemed as most important. This idea of dimensionality reduction, just to maybe quickly mention it here, is the idea that we start with something with high dimensions, and as we change the representation, we'd also like to change the number of dimensions that describe that representation. If we can cut that down to smaller, all the better. Now, in the assignment that you did, you started off with 14 features, and you wanted to come out with just a single binary. It's this class or it's this class. So you're effectively saying you're reducing 14 dimensions down to just 2 dimensions. Ideally, when we start with so many dimensions, and you saw even with a very simplistic image of 32 by 32 by 3, we have 3072 dimensions. If you start with an image that's 224 by 224 by 3, you can see there that you're going to have a huge number of dimensions, and you might want to, on the output, just have 1,000 different classes of item that you want to suggest it is. So you've got to reduce the dimensions down from very, very high to something quite small. Just like the representations, you don't want to do that in one single jump like you would be doing, like you would have done in your last assignment. You'd like to do that slowly. So slowly reduce the dimensions by changing the representation into a more compact way of doing it, and having a smaller number of dimensions in each case. Convolutional neural networks can do or incorporate both into this. Can and do incorporate both is what I was trying to say there. Each layer can learn a new and improved representation, but it can also learn to reduce the dimensionality in each case. The most straightforward way is to just basically reduce the dimensionality of the X and the Y in each particular case. Now, what we tend to find is that we reduce the dimensionality spatially, and we sometimes increase the dimensionality in terms of the number of filters that we have in each layer. But we eventually need to reduce that down as well, so that we end up with with a reasonable output at the end. So the most straightforward way to do this is with a pooling layer. Here we take a section of pixels and reduce the number based on some criteria and by a predetermined amount. So one example is max pooling, which is very useful in terms of this idea of correlation, where we only really want to take the maximum one and say that's what we've decided for this area of the image that we're taking, and another one then is average pooling. So in this case, over 2 by 2 here, we would say, well, 76 is the biggest one, so we put that in for that. In this 2 by 2, we can see that 66 is the biggest one, so we keep that. Discard the rest. Here the biggest one is 41, so we put that there, and here the biggest one is 61, and we put that there. Okay, particularly useful in classification and recognition type networks because they're big into their correlation. Average pooling, it was used early on in the feed-forward recognition networks, but not used so much anymore. But it is still used in generative networks and so on. So here we have an example where we take the average of those 4 numbers, put it in as 45. The average of these 4 numbers, we put that in as 54. The average of these 4, and we put that in as 26.5, and the average of these and 52.5. Okay, so that's how you would reduce it down now. Instead of having a 4x4, which is 16 dimensions, we now have just 2x2, which is 4 dimensions. So that's one way of doing this dimensionality reduction. The other thing you can do is you can use convolutions, so 3x3 or 5x5 or whatever you're going to do, but do a stride of greater than 1. So maybe a stride of 2, so you jump 2 pixels before you do each set of calculations, and that's going to give you a smaller activation map on the output. It'll effectively reduce it by half in each case. So to some extent, the idea of simply using convolutions with a stride greater than 1 has become popular for this downscaling idea. In generative networks, there is sometimes a need to upscale, and this can be achieved with fractional convolutions, sometimes called deconvolution or transpose convolutions. Now, one thing that concerned me, obviously coming from a DSP and from a computer vision background, was that we would do this downscaling either by max pooling or by these strided convolutions, and we would do no sort of anti-alias filtering before that. That's not something that happens. Again, I think it's probably because of this idea that that we're really only doing correlations and we're not going to be too concerned about that. But the other idea, of course, that people will often give us an answer to this is, well, you can just if you're doing it by convolutional filters, the convolutional filters have to learn that anti-alias filter into it if it's useful to do so, and if it's not useful to do so, it doesn't learn it into it. Okay, more than that can't really answer, but certainly there doesn't ever seem to be any sort of anti-alias filtering before it does any of this downscaling. So whatever the method of downsampling, they all have the potential to learn dimensionality reduction. So let's take a typical ImageNet scenario where we start with images that are 224 by 224 by 3, and we must eventually end up by giving a prediction of 1 out of 1,000 class labels. Okay, so we've got 1,000 different class labels, and we have to be able to say it's most likely this one and less likely this one, and a load of them should be something close to 0. But we start off with very high dimensions. Let me just see, 224 squared multiplied by 3. Yeah, it's 150,528 dimensional problem, and we would need to reduce that down to 1,000 class labels. We don't want to do that all in one go, so this means that we want to reduce the dimensions. Oh geez, that actually the calculation done. Let me go and do it again on a calculator. So 150,528. We need to bring that down to 1,000. It obviously makes sense to reduce the dimensions progressively while also changing the representation. So you'll see a general trend towards doing something like a convolution activation, then do a pooling layer, then do a convolution, an activation, and a pooling layer, and then do it again. And we slowly bring this down, and we decide how many of these convolutions filters we're going to have in each case, and we bring it down that way. The other thing you might sometimes see is convolution activation, another convolution and activation, and then then have a pooling layer. And as I said, there's also a trend then towards this idea of having convolution activation and then a strided convolution to bring it down in some way and slowly reduce the dimensions. We previously discussed the idea of using hand-engineered features to change the representation of data to make it easier to use in a standard machine learning algorithm. The convolution layers and the pooling layers are also used to bring the dimensionality and representation to a form that allows it to be input to some familiar machine learning mechanisms like we saw in the beginning of the semester, such as logistic regression, or when we extend logistic regression to multiple classes, we call that a softmax. Or you can have a multi-class SVM or something like that as well. So we want to be able to introduce it or put it into one of those. We've got to reduce it down to dimensionality and to a representation that makes sense to put it into one of those. To do this, we normally use a fully connected layer, sometimes called a dense layer, after all the convolutional layers have finished, and before the output activation. So this final general machine learning bit that sits on the top, classical machine learning bit that sits on the top, normally uses a fully connected layer for that, so not convolutional. So we'd like to have our convolutional dimensions down to a very small level, very small number by that stage. So we'll often have this where we'll do our standard kind of convolution, activation, pooling, do it again, and then eventually come to a fully connected layer and then into something like an SVM in order to do our final classification into one of 1,000 classes. This could also be a binary classifier, obviously, in which we just have one of 2 classes that we could have out. Depends on the application that we're trying to do. So, lovely image here by Andre Karpathy, and if any of you that were that did the multiple view geometry and computer vision with me last year, in the final lecture we did a little bit about Tesla's autonomy day, and one of the guys that got up to speak was this guy Andre Karpathy. So he originally worked with Stanford on developing the course, the CS231N course, which is very, very useful. So all the notes were developed by him, and this is an image that comes out of those notes, and I think it's a really nice image for describing what's going on. It doesn't show the entirety of this network, but what it does show us is 10 activation maps coming out of a convolution. So we've got 10 filters in each case here for each layer. And what we do is we look at the image here, and you can see the pixels that have been created by after the convolution, and we then pass through a ReLU activation. Now I'll talk about the ReLU activations next week, but that's a nonlinearity, and we can see the effect that the nonlinearity has had. It's removed an awful lot of the unimportant things and just left us with what is important. Once again, we go through another convolution and then through another ReLU layer here, and you can see that it's really only interested in some small number of these here. But you can see that some of the other filters are interested in other things. They're interested in this bit here. This filter not interested in much at all. This filter is quite interested in some stuff. So you can start to see that some of the filters are interested in things. And what you might find is that if you put something like a cat image into this, that some of these other filters would light up much more than the ones that are lighting up for something like a car. And then, of course, what we do is we go through a pooling layer, and you can see that what's happened here between this and the pooling layer is that it's really just reduced the dimensionality of this. We've a smaller number of dimensions. And this continues on. We keep having these filters that only pop up in places now. It reduces our dimensionality each time we go through these pooling layers until we eventually end up at this output where we have, as you can basically see here, you can see each of the individual pixels. It's basically ended up with a 4x4 here. And what we then have is we would have a fully connected layer where the softmax or the SVM for a car would basically have a connection to every one of these and every one of these as well. So it would actually have quite a number of parameters that it would require, and that would give us the probability that what it's seeing is a car. We then have a separate one for a truck, separate one for an aeroplane, and a separate one for each of the other ones. And what we then do is we look at the probabilities over these and say, well, which one came out the highest? If it's a little bit unsure, then some of these will be quite close to each other, and if it's very sure, one of these will be very high and the rest will be very low. And so there's often a thing where they look at the top 5, in other words saying, okay, you didn't get it in the top 1, but did you get it in the top 5? Okay, so if you've got it in the top 5, then we're giving you a score for that and so on. So what are they learning? So to determine what the network layers are learning, there are a few methods. We can look at the filters. Now we're looking at the activation maps here, not at the filters, but we can look at the filters. If these look like hand-engineered filters from the literature, then we already know what they do, and therefore we can figure out what they've learned. Maybe they've learned edges or they've learned something else. We can look at the activation maps, and that's what we're looking at here. And we can see what parts of the images light up at different points in the network and for which inputs. The other thing you can do is you can hallucinate. So you can make your network hallucinate back the way into an image, which is what we have in the title slide. And you can also do that in just a random noise image to see what we've got there. So using a random noise image as input, take the filter somewhere in the network and try to maximize its response by doing gradient ascent on it this time. Trying to make it larger with respect to the noisy image. This means the image is modified to give a large response from a particular filter. only the image changes, and you can also start with a known image and hallucinate from there, which, as I said, is what we have in the title slide. So it's what I've done to the picture of Ben Bulbin there, and you can see what this filter likes, and it changes everything to look like that filter. So we're nearly done, folks, don't worry. Okay, few resources for you here. Francois Chalet, that I mentioned last week, he implemented the Keras system, but he has a nice thread that he did on Twitter, and then somebody turned into a kind of a blog post that shows you how to use Keras with TensorFlow 2. And the other thing is, if you'd like to do a bit of this hallucinating stuff, you can play around with the Deep Dream generator there as well, and have a go with that. So what I'd advise you to do, with a little bit of a lull before you come to your next assignment, what I advise you to do is to look at that thread by Francois Chalet and see if you can set up one of these deep learning networks on Colab. I think he even has it set up for you there. You can just click on it and play with it. Have a little bit of a play around with that and make sure that you're comfortable with it, because the next assignment that I give you as an individual assignment, you're going to be doing a little bit of playing around with these deep networks. Okay, I'm conscious of the time, and I know you have class at 7:30, and so do I. So I'll say goodnight to you at that.